In the early 1900s, geology explained Earth in pieces. Mountains rose here, volcanoes erupted there, earthquakes struck without a shared reason. Scientists mapped rocks and described layers, but the big question stayed open. What tied these events together? Most experts treated continents and ocean basins as permanent fixtures. Land sat where it sat. Oceans stayed put. Earth looked built, not busy. That fixed picture started to crack when patterns refused to stay local. Coastlines seemed to match across oceans. Similar fossils and rock types appeared on shores now separated by thousands of kilometers. A German scientist named Alfred Wegener followed these clues and reached a blunt conclusion. The continents once belonged together. They later separated. In his view, the map was a before and after story. Wegener called it continental drift, and it rewired the problem overnight. If continents moved, then oceans and continents stopped being background scenery and became part of the action. Mountain building, earthquakes, and volcanoes could finally share a cause, at least in principle. But his claim also demanded something no one had yet shown, a real process that could push entire continents across the planet. In the 1920s and 1930s, Wegener's drifting continents ran into a hard wall. Many geologists accepted that coastlines and fossils looked connected, but they demanded a working engine, not a suggestion. What could possibly shove a continent across the planet? Every proposed force sounded too weak or too vague. Worse, the seafloor looked like a solid barrier without a mechanism. Continental drift stayed outside the mainstream. That rejection carried a consequence. If continents could not plough through ocean crust, then the key had to sit somewhere else. The deep ocean became the obvious blind spot. For decades, it had been more assumption than evidence, because almost nobody had measured it in a systematic way. Now that began to change. Researchers and institutions invested in oceanographic surveys, taking soundings, samples, and physical measurements over wide areas. This shift did not rescue Wegener's idea right away, but it redirected the search for answers. The ocean floor stopped being empty space on a map and started looking like data waiting to be collected. If Earth had a large-scale process that built mountains and set off earthquakes, it had to leave a signature somewhere. And the largest, least explored part of the planet offered a place to test it. The next clues lay underwater. In the 1940s, the push to fight a world war quietly changed Earth science. Navies needed to find submarines, so they poured effort into sonar, sound pulses sent down, then timed as they bounced back. Each echo turned into a depth reading. Line by line, ships traced the seafloor in a way no one had managed before. What had been guessed from a few scattered measurements became maps, and the maps carried surprises. When wartime tools moved into peacetime research, the ocean floor stopped looking like a flat, featureless basin. Long rises and deep cuts appeared where people expected smooth plains. Survey tracks from different oceans began to match up, as if separate puzzles belonged to the same picture. Scientists saw that one enormous mountain chain ran through the oceans, not in one piece, but as a connected system. It wrapped around the planet, mostly hidden underwater. At the crest of this mid-ocean ridge, many profiles showed a split down the middle, a central rift like a long valley pulled open along the top of the rise. That detail mattered. A rift suggested tension, cracking and change, not a seafloor that simply sat there forever. The ocean floor now looked like it had seams, and once you noticed seams, you started asking what force could be working on a global scale. In the late 1940s, the seafloor no longer looked like a blank plain. Now researchers asked a sharper question. Where was Earth actually releasing energy? They lowered instruments to measure heat leaking up through the ocean floor and compiled growing catalogues of earthquake locations from around the world. When the numbers went onto maps, the surprises did not sit in the middle of oceans or continents. They lined up. The hottest readings tended to follow the mid-ocean ridges. Earthquakes too tracked those ridges, but they also formed tight bands along deep ocean trenches and along long mountain belts on land. This was not random noise, it was geography with a pattern. The same narrow zones kept showing up, whether the measurement came from a thermometer in the sea floor or a shaking seismograph. At first, ridges, trenches and mountains looked like separate problems with separate causes, but the maps argued otherwise. These belts connected, sometimes running for thousands of miles, crossing oceans and wrapping around continents. The simplest reading was unsettling. Earthquakes and heat flow did not just mark local trouble spots. They traced a linked system powered by motion deep inside the planet. By the late 1950s, seafloor surveys stopped being simple outlines and started becoming real maps. And they revealed something unsettling. Long, narrow gashes in the ocean floor, deeper than any nearby basin. These trenches did not appear randomly. Again and again, they sat beside curved chains of islands or coastal volcanoes like a matched set. The ocean floor looked organized, built around lines of extreme change. Then the earthquake records tightened the pattern. The strongest shaking clustered around those same trenches, and it did not stay shallow. Quakes traced sloping zones that seemed to dive down into the earth step by step from the trench toward the volcanic arc. That geometry mattered. It suggested movement, not cracking in place. Something solid looked like it bent downward and carried earthquakes with it as it sank. That forced a new idea into the conversation. If new seafloor was being made somewhere, it also needed a place to go, or the planet would have kept expanding. The trenches offered an answer. Scientists proposed subduction. Old oceanic crust slid into a trench and descended back into the mantle, disappearing from the surface. It sounded drastic, but it recycled the seafloor and linked trenches, volcanoes, and deep earthquakes in one motion. By 1960, the big question shifted from what the seafloor looked like to what it actually did. Geophysicists started building simple models of mantle convection, slow, circulating motion in the hot rock deep below. If the mantle could creep and flow over millions of years, it could drag the surface with it. Suddenly, the ridges were not just bumps. They looked like places where the planet's interior pushed upward. Then, an American geologist, Harry Hess, took that moving mantle idea and made it practical. He focused on two stubborn facts. The mid-ocean ridge system ran across the globe, and the ocean floor seemed surprisingly young. Hess argued the ridges acted like long cracks where magma rose, cooled, and became new ocean crust. That single move turned the ridge from a mystery into a factory. In Hess's picture, the seafloor did not sit still after it formed. It spread away from the ridge on both sides, carried outward like a conveyor belt. The farther from the ridge, the older the crust became, until it reached the deep ocean trenches. There it could sink back down, clearing space for more crust to be made. Creation at ridges, motion across oceans, recycling at the edges. By 1963, seafloor spreading sounded plausible, but it still needed a clean, measurable test. That test came from magnetism. Basalt formed at mid-ocean ridges contained tiny magnetic minerals. As the lava cooled, those grains locked into place like compass needles, freezing the direction of Earth's magnetic field at that moment. The seafloor, it turned out, carried a magnetic memory of its own birth. Earth's magnetic field had not stayed the same through time. It flipped again and again, so magnetic north sometimes became magnetic south. When ships towed sensitive instruments across the ocean, the readings did not drift smoothly. They jumped in bands, a strip with stronger than expected magnetism, then one with weaker, then stronger again. These stripes ran parallel to the ridges, as if the crust had been stamped in long alternating lines. The crucial detail was symmetry. The same sequence of magnetic bands appeared on both sides of a ridge, matched like mirror images. That pattern fit one simple process. New basalt formed at the ridge, recorded the field direction of that time, then moved outward while newer lava took its place. Each reversal drew a new stripe, left and right at once. Spreading stopped being an idea. It became a measured record. By the mid-1960s, seafloor spreading fit the magnetic stripes, but it still left a basic problem. Mid-ocean ridges did not run as one clean line. They broke into offset pieces, like a cracked zipper. If new crust spread outward from each segment, how did those segments connect without tearing the planet apart? The map looked messy, and the motion looked impossible. Something important was missing. The missing piece came from earthquakes. Geophysicists noticed a strange pattern along the short lines that linked offset ridge segments. Shaking did not spread through the whole offset the way people first assumed. It stayed locked between the ridge tips. That behavior matched a different kind of boundary, a transform fault, where two blocks of crust slid sideways past each other. The earthquakes traced the sliding, and the geometry finally made sense. With transform faults in place, the seafloor stopped being a set of disconnected features. It became a working system. At ridges, fresh ocean crust formed and moved away. Along transforms, that moving crust shifted sideways to line up with the next spreading segment, and at trenches, old crust disappeared back into the earth. Creation, sideways transfer, destruction. The ridge trench world now linked up into one global network, and it moved as a whole. By 1967, the pieces no longer sat as separate ideas. Seafloor spreading, subduction, and transform faults pointed to one bigger picture. Earth's outer shell acted like a set of rigid slabs. Scientists called them plates. They moved across a globe, not as drifting continents alone, but as linked blocks that carried oceans and continents together. That simple shift changed everything. It turned scattered clues into one working system. With plates in mind, boundaries became the key. Where plates pulled apart, new seafloor formed and volcanoes lined the ridges. Where they collided, one plate sank. Trenches deepened, and earthquakes cut down into the planet. Where they slid past, transform faults produced sharp, shallow quakes in narrow belts. The theory did something geology had struggled to do. It predicted where the action had to be before anyone looked. Into the early 1970s, researchers drew the first global plate maps and watched old arguments fade fast. The fit was too good. Earthquake belts traced plate edges, volcano chains followed subduction zones, and mountain ranges rose where plates crumpled and thickened. Many lines of evidence that once competed now supported the same framework at once. Plate tectonics became the unifying rule book. It explained not one mystery, but many in a single motion. By the time plate tectonics settled in, the question changed. It no longer asked whether plates moved, but how fast and what that meant for people. Satellites and GPS geodesy turned the surface of Earth into a measured grid. Points on different plates shifted year by year in millimeters. The motion stopped being an inference from old rocks. It became a live readout. At the same time, earthquakes became more than dots on a map. Modern seismic imaging used waves from quakes like a medical scan, revealing colder, denser slabs diving into the mantle beneath trenches. Subduction stopped being a clever explanation and became something tracked in 3 dimensions. Where a slab bent, tore, or stalled, the deep engine showed itself. With motion measured and the interior imaged, plate tectonics moved from a solution to a tool. Hazard forecasting used plate speeds, locked faults, and boundary geometry to estimate where strain built and where it released. Earth system science linked shifting plates to oceans, climate over geologic time, and the cycling of carbon through volcanoes and burial. In the early 1900s, mountains and earthquakes lacked one engine. Now one framework drove forecasts, models, and decisions.